right, so hi, welcome. Thank you for joining us to our webinar. We are dedicating this one to our SiC Inverter platform. CISSOID at a glance. Who are we? Where do we come from? CISSOID is a company spun off out of the University of Louvain-la-Neuve in Belgium in 2000, dedicating the expertise to high temperature electronics. From that, we investigated silicon carbide early on in 2009, 2010. We started to look into the technology and developed our own gate driver IC chipset. From that, evolved several discretes and modules. From there, made the second generation of our gate drivers, developed intelligent power modules. From that, gate driver boards, evolved the power modules, developed a control module, and brought out several reference designs, which we will discuss in more detail today. The markets we play in are anything automotive and around it. So, of course, our heritage is high reliability, high temperature. So we go into aviation, heavy duty vehicles, marine applications, but also transport like buses, trucks, high performance cars, more and more autonomous vehicles as well. And of course, industrial motor control. So starting off from our power module, we integrated the gate driver chipset on top of that, making it an intelligent power module. As far as I know, correct me if I'm wrong, the only silicon carbide intelligent power module on the market in this power range. We will go into a little more detail there. We evolved, as said, a control board on top of that, engineered reference designs and a complete platform around it, running also the necessary software on top of that, so making it a complete ecosystem for an inverter solution. The intelligent power module. So the power module itself is a three-phase module, meaning it has two half bridges, 6 switches integrated. It's 1200 volt silicon carbide, low on resistance, of course, depending on how many MOSFETs are within one switch in parallel. Also determining the maximum continuous current available through that module, attaining fairly high switching frequencies. Typically in applications, we see 12 to 16 kilohertz, sporting high isolation grade and low switching energies, as you can see from the table, of course, also dependent on how many switches are in parallel. And the modules come with a lightweight ASIC base plate, either in a pin-fin version for direct liquid cooling or a flat base plate for whichever cooling you prefer. The IPMs have been developed to be thermally robust. This is our know-how to assemble and manufacture modules that can withstand harsh environments. Of course, the junction temperature of the silicon carbide is 175 degrees C. Junction to fluid thermal resistance is 0.16 degrees per watt. Junction to case 0.119 degrees per watt, and the complete assembly, so this includes the gate driver board, are designed to work up to 125 degrees C ambient, continuous. And on the right hand side, you see a screenshot of our calculation tool where you enter parameters like the bus voltage, fluid temperature, switching frequency, which then shows you where you end up and which power module is the one suitable for your application. So these modules are based on our second generation gate drivers. They deliver high peak currents for fast switching. They are robust against high DVDTs. As mentioned, the assembly is designed to work at 125 degrees, as you may know if you have experience with it already. The gate drivers can develop quite some temperature on their own in high switching frequencies, so the whole assembly is optimized and designed for that. The gate driver chipset also supports hardware protection functions like UV-LO, desaturation detection, soft shutdown, active Miller clamp, glitch filter, anti-overlap protection. So these protections are available in hardware and have already saved quite some test hardware, as we've seen when customers go through evaluation tests and calibration phases. And I probably forgot to mention this at the beginning. If you have questions, please enter them into the Q&A chat, and we will come back to them if the topics have not been covered during the presentation already. So this brings us to the inverter control module. The control board was developed on top of the IPM. So we have the power module, the gate driver board, and stacked on top of that is the control module. Now this, the control board. This board was developed around the T222 adaptive control unit by a company, a French company called Silicon Mobility, which have been acquired last year by Intel. So in the meantime, it is an Intel automotive processor, but this processor has been developed as an application-specific processor, meaning it's really tailored to work well for motor control applications. The inverter control module has all the necessary interfaces, of course, both for the power modules, the motor vehicle communication, and of course, development and debug interfaces. And with that processor also comes a complete suite of software, which we will go into a little more detail in the next slides. So the T222 ACU is a processor built around a core, dual core Cortex R5F based, working in lockstep for safety reasons. But very specific about this processor is the advanced motor event control unit. This is a hardware block containing all the interfaces plus a flexible logic unit, an FPGA-like structure, which can be programmed. This means that processing of the communication and interface with the motor can happen in parallel in hardware, offloading the core, meaning it's a really fast solution and enabling fault detection, correction, and containment of it within tens of nanoseconds, typically between the 10 and 20 nanosecond window. So it's much faster than standard MCUs who have to process everything in software, and it's also completely timing predictable. With that comes the adaptive control application. That is a complete motor control solution. It supports various motor types like permanent magnet, wound rotor, axial, 3-phase, 6-phase, different types of modulation like space vector, continuous, discontinuous, of course, variable switching, and also comes with options like dead time compensation and optimized pulse patterns, which we'll discuss in more detail. Various motor position sensors are supported, of course, and specific algorithms are in the software suite like flux weakening, field-oriented control, torque derating, and so on. The core of the software is locked, but there is an API available which allows you to build an application layer on top of the software, making it your own control unit. So you have access to torque, speed, current control, the motor state, getting the motion state. Is it braking? Do you have to reverse charge the battery? All that control is available, and of course, complete access to the safety functions, diagnostics, and configuration for calibration and so on.
Just wanted to emphasize that this software really brings a lot of options compared to off-the-shelf inverters, and a lot more flexibility. You have access to a lot more parameters, and also during debug, you can access everything which is happening in the CPU. So it's a complete different level of transparency at software level.
Mm-hmm. Yes, indeed. Our solution really sits in between getting all the hardware from various suppliers and getting an off-the-shelf component, where we bring a complete proven solution that you can then start to customize. A word on certification and availability. On the Intel Silicon Mobility side, the processor and both the software are ISO 26262 ASIL-D certified. The processor is an AEC Q100 grade 1 component, and the software is AUTOSAR 4.3 compliant. On our side, the inverter control module is nearly ASIL-C ready. We're about 95% through that process and should be finished within a couple of weeks. We're going through the AQG 324 automotive qualification for the entire module, which is slated for the next month. And later on, the intention is to be fully ASIL-C certified around about the summer.
Mike, there's a question on the chat.
Okay.
Can the switching frequency be increased to 60, 70 kilohertz?
I will let Pierre answer that one.
Yeah, so there is no intrinsic limitation to increase the frequency, but this need to be validated, and it also depends, let's say, on the operating points of the inverter. So this is something we need to discuss in detail with the customer.
Okay, thank you, Pierre. I'm almost there to hand over to you for the more technical side. So lastly, indeed, as mentioned by Emmanuel, we have developed a complete platform around the module. You see here the DC capacitor that was designed with the bus bar on top, specifically by a company called Advanced Conversion, with different ranges of capacity and voltage, meaning this is a completely tailored solution. It's designed to work well together. We have a full characterization of the switching loop, and the total loop inductance is typically 80 nanohenry or below that, with the full assembly rated to work up to 125 degrees C. So really optimized to support bus voltage up to 800 volts, and bringing the best trade-off between switching energies and voltage overshoot. And for evaluation purposes, we also have 3D printed reference coolers available that you can either print yourself or can acquire from us. And this brings us to the reference designs, where I will hand over to Pierre.
Hello,
Yes, you should have control now, Pierre.
Yeah, okay.
Okay.
So good morning and good afternoon to people joining from Asia. So let me now introduce our SiC inverter reference design. So this SiC inverter reference design has been developed to further help our customer accelerating their SiC inverter design. They are built around our SiC ICM to support high voltage and high power designs. Thanks to the bill of material and the 3D step file, so people can modify the mechanical design according to their requirements. And as they are running the ASIL-D control software, they can be safely used on a motor bench or in vehicle. They can be set up and calibrated in less than a week on a motor bench. So two options are available. First, the benchtop options that is optimized for lab and bench testing with an easy access to all the connector on the front face of the inverter. And then you have the onboard inverter, which is more compact and more robust and is meant for in-vehicle testing.
There's a question, Pierre, about the cables and the filtering. Do you also provide over voltage suppression filters when long cables to the motor are used?
So far not, but so this is something we generally address at the let's say, beginning of the support stage. So when we prepare the on-site support, we discuss with the customer about the length of their cable and if there is eventually a risk for their motor due to the high DVDT, because it's a hot topic with SiC inverters. So as you have high DVDT, there is a risk of overshoot on the motor. And so some customers are asking us to start with some testing to make sure that the overshoot on the motor are acceptable. And of course, it depends on the length of the cable. But so I propose that we keep the question for the end. So there is a Q&A session at the end, and so we'll answer to all the questions at that time. So regarding the benchtop reference design, so it can support testing in the lab up to 850 volt and 330 kilowatt peak. So as I explained, it is built around our SiC ICM, and we add the three-phase current sensors, of course, the DC link capacitors. There is a PCB with the Y caps and passive discharge, an EMI filter from TDK, and the circuit for the liquid cooling. 4 models are available depending on the voltage and power ratings. The onboard reference designs in peak condition can deliver power up to 350 kilowatts, phase current up to 600 amps, and it can support switching frequency up to 50 kilohertz. With a volume of less than 7 liters, it can support power density of 52 kilowatt per liter. To support EMC designs, we are delivering to customers a complete SPICE model of the power stage of the inverter, including the modeling of the parasitic elements, like the stray inductance of the power module or the parasitic capacitance to the chassis. It includes also an accurate modeling of DVDT, DIDT, and voltage overshoot, which is key for EMC optimization. And the simulation bench should also include a truthful model of the AC cable and of the motors. With everything in place, you can extract the frequency response of the differential and common mode noise and compare it with the CISSOID limits. Our FAE team can support on-site evaluation of the inverter on a motor bench, going through several steps, starting with the configuration of the project software according the motor parameters. Secondly, the inverter motor and hardware is set up, taking care on all the interface, including the sensors, the digital interface like the CAN or the safety line, and the power and cooling connections. Then the system can be calibrated going through different modes in order to set the calibration parameters for the position sensor and for the speed regulator. Finally, the inverter and the motor can be characterized at different set points. And for example, an efficiency map of the motor can be extracted. So you can see that we've demonstrated inverter efficiency in excess of 99%. Here we compare our SiC inverter with an IGBT1. So as expected, you can see that the peak efficiency is higher for the SiC inverter, but also, interestingly, the SiC inverter can maintain high efficiency even at low torque and low speed. Here we show a very good example of the potential of our solution with this EPTO system for electric power takeoff developed by our customer Hydroluduc. So developing around our SiC inverter control module, they've been able to develop a highly compact and highly efficient system. Now let's discuss some features of the control algorithms, like the dead time compensation. So the dead time compensation is part of the Intel Adaptive Control app, and it is included in the SVPWM module. The goal of the dead time compensation is to correct the duty cycle to compensate the effect of the dead time, which includes output voltage loss at the fundamental frequency, low frequency harmonics, current and torque ripple. The compensation is proportional to the DC bus voltage, the switching frequency, dead time, MOSFET T on and T off. A case study has been presented at the Compel workshop on control and modeling of power electronics, and the characteristics of the inverter and motor used for this study are summarized in these tables. The impact of dead time compensation has been first demonstrated through LT-SPI simulations. As can be seen, the amplitude of the signal at the fundamental frequency is higher with dead time compensation, and also the amplitude of the harmonic is reduced. And this has been confirmed by measurement on a motor bench, demonstrating an improvement of the THD by almost a factor 2. Another powerful feature of the control algorithm is the optimized pulse pattern. So OPP, it's a method replacing conventional modulation like SVPWM or DPWM. So it is based on the electrical angle, so it's not a time-based modulation. And OPP applies switching pulse pattern repetitively at each electric period. So as there is no PWM carrier, you have the full freedom to locate the switching pulse at any angular position. So it's important also to understand that the optimization is made for a given speed and torque range, and also that the OPPs are generated offline by digital processing. And with our SiC inverter platform, you have a ready-to-use solution to run Intel high-performance OPP modulation algorithms. With OPP, the number of switching pulses and their related position are determined to optimize the modulation upon different criteria, like the inverter and e-motor losses, the THD and 8VH, or also the current ripple. At the motor and inverter level, OPP brings a lot of benefits, like a 5% gain in efficiency in critical load points. It also is the control of a high-speed motor. Thanks to the extended overmodulation, you can get an increase of the torque by 20% for the same motors. You can optimize the noise behavior, and at benefit level, you have cost and weight saving thanks to the downsizing of the motor or the inverter. You can also lower the battery voltage and reduce the requirements in terms of sound insulation. So let me summarize now this presentation. So we've presented a unique solution for the development of SiC inverter with a modular and open platform. The solution is proven, so it can be rapidly tested on a motor bench. If necessary, it can be easily modified to fit with customer requirements. We address all the elements of the inverter design, from components to software, with a single point of contact for the support for the hardware and the software. So thank you for your attention, and now the session is open for questions.
Pierre, to start with, I think we can address one of the questions that was raised during the presentation. Do you also have sensorless algorithms for the motor control?
Okay, so that's a good question. So our partner Intel has developed some, let's say, prototype of the software to address sensorless control, but it is not yet available as part of the standard software. So it's really a case-by-case, let's say, study that we have to make with the customer. If there is other questions. So do not hesitate to put your question in the chat.
Hello, this is Teddy Bonin, FAE at CISSOID speaking. I see questions in the Q&A.
Those were already addressed, Teddy.
Okay.
Yeah.
Thank you, Emmanuel.
So I see another question is, there a trace port mandatory for a Lauterbach unit for calibration and debug?
Okay, so I can answer to that question. So indeed, for the moment, you need an high-speed interface like a Lauterbach to run the calibration process during the calibration week. After that calibration week, the customer is independent from the Lauterbach and can control the inverter through the CAN interface. And we are currently developing a solution to make customer independent of the Lauterbach even during the calibration week. And that will be available in principle in Q3 or Q4 this year.
And maybe a final one, as we're running into the time limit. What is the licensing scheme for the software?
Maybe Emmanuel, you can answer to that question.
I can answer this one. So we have two different types of license. One is the binary code license. The purpose of the binary code license is for lab testing. So for initial testing, it's less expensive. So it's a good way to have a quick test in the lab. And we have the object code license, which is more comprehensive, contains all the features and gives access to the API layer. And this is also suited for production, which is a one-time payment license for the project lifetime. So that's the way it works. So we have those two options: binary code or object code license.
Okay. I see one more. You have mentioned one can get 20% more torque. Can you explain more on that?
So that's mainly related to the extension of the overmodulation thanks to OPP. So you can reach a modulation index of 127, and so with the same motor you can push the torque limit, let's say, without making the motor more powerful.
Okay. Any more questions? No. All right. That concludes the webinar. We're right on time. Thank you very much for attending. We will send out the link to the recording later on, and if you have any further questions, please feel free to contact us. Thank you. Bye.
Thank you, everyone. Thank you. Bye.
Thank you. Bye-bye.
Thank you, everyone.
Bye-bye.
Bye.